ended up being a rumor. Nevertheless, we used the double focusing mass spec at MIT to analyze the off gas of one of our cells. So in the bottom frame, this is an electrolyzing D2O cell. The top frame is the ambient air in the room that the electrolysis is taking place in. In both cases, you can see we can easily resolve the helium-4 and the D2 mass peaks here. In both cases, in the control as well as the experiment, we see no difference in the height of the helium off-gas peak. We've also done quite a bit, a significant amount of tritium counting. This is for the cells that I've shown you here today. This just one slide, although we've done actually quite a bit of this. The initial tritium count, 101 disintegrations per minute per milliliter. At the end, 137 decompositions per minute per milliliter. The uncertainty we feel based on the spread of data for a number of cells is plus or minus 15%, and we conclude no significant increase in the tritium concentration in this, or in fact any of our other cells. Interestingly enough, the tritium level suggested by the manufacturer is only guaranteed to be less than 300 disintegrations per minute per milliliter. The calorimetry that we've done is slightly different than has been talked about so far today. It's a constant temperature, steady state kind of calorimetry. We have a heater in our cell, you'll remember from a previous slide. So there are two sources of power into the cell, power from a heater as well as power to the electrolysis, to the electrodes. There are two sources of leak. There's a heat leak, an intentional heat leak to the constant temperature bath surrounding the cell, as well as a leak to the production of hydrogen and oxygen. This equation here shows an increase in some excess power, an unknown origin, plus the heater is equal to a constant, which is the heat leak, plus the IV power, plus the electrolysis, or minus the IV power, plus the electrolysis power. And so the calorimetry is based on a decrease in heater power being equivalent to an increase in a new source of power in the cell, these being constant throughout the period of the electrolysis. So we simply look for a decrease in heater power, and we say that that's equivalent to an increase in an unknown process. I've shown here a small portion of our data. We take data every second, or every 2 to 3 seconds. So we have a full cell history of all the data for all of these cells. This is just a small portion running an hour and a half after the cells were turned on for 200 hours. The top frame here shows the temperature, that we're able to control the temperature inside the cell. Remember, this is done isothermally, to plus or minus 50 millidegrees C. The bottom frame shows the cell current, which of course is the same since in all cases we're controlling the current. The next slide at the top shows the cell voltage, that these are matched as they should be since we claim that the cells that we're using are matched. You'll notice a slight difference in the cell voltages. This is just a reflection of the difference in electrolysis potential required for D2O and H2O. But the key piece of information is shown at the bottom. That's the heater power, and within a very conservative error resolution of 9%, we suggest that there's no significant change in the heater power during this portion of the experiment or any other portion of any other experiment within our error limits. Again, 9% seems a lot. It's certainly nowhere close to the precision calorimetry that was talked about earlier today by Professor Appleby, but nevertheless, well within our range that we should be able to see the types of heat gains claimed by Pons and Fleischmann and others. I don't think I can stress enough the importance of looking at fusion products rather than in addition to heat gain, since after all, this is a cold fusion workshop. Our analysis, we have analyzed all of our palladium cathodes for helium. Interestingly, I'll just run through this calculation for just a minute here. The absolute detection efficiency is 4 times 10 to the 11 atoms per cubic centimeter. We can calculate the heat of reaction from DD goes to helium-4 to be 3.8 times 10 to the minus 12th joules per helium atom formed. For chemists, that's a staggering number of 260 gigacalories per mole. The upper limit, then, on energy production is shown here. And what this corresponds to, then, is an excess power, minimum detectable excess power, using helium analysis of 1.8 microwatts per cubic centimeter. So if you assume that any excess heat comes from a process involving helium, then the ultimate calorimetric resolution by analysis of helium is 1.8 microwatts, which is very low indeed. Make a few more comments about this. The nice thing about the helium analysis, so we can detect fusion powers, as I said, on the order of a few microwatts. Helium analysis is reaction specific. DD goes to either helium-3 plus a neutron or helium-4, and the method is unambiguous and can be done quite quickly. Kurtz and Jenkins at Woods Hole Oceanographic Institute have run some of our analysis, as have the people at Sandia and Rocketdyne. Kurtz and Jenkins have asked that we inform the audience that if anyone wishes to have one of their rods analyzed for helium, that they'd be happy to do that. You can go through us or contact them directly for a helium analysis in palladium. 1 minute, okay. Okay, that's good, because that's how much I have left. Okay, so I want to, for our helium analysis, in which case we've seen nothing above background for helium in any of our palladium cathodes, I just want to show this slide here to acknowledge the help of Rocketdyne and Sandia in getting this particular set of data together for us. Here's a summary of the work that we've done, things that we've looked for. Moderated BF3 neutron detectors, we can see less than 40 neutrons per second. That's 34 times higher than that result reported by Pons and Fleischmann. And we have no result to show here, no positive result. The gamma ray spectroscopy, same, no result. Constant temperature calorimetry within our error limit of some 9%. Again, no significant new excess heat. The tritium concentration in the electrolytes and the controls, no significant change. High resolution mass spectroscopy of the effluent gas at background level. Comparison of D2O and H2O cells operating of similar construction, operating in parallel, the same within 9%. And now we can add to this our helium results of our palladium cathodes. Finally, I'll leave a slide up here while I take questions. And this is, we've learned 2 or 3 things. We've learned that it's possible to do an experiment at a place like MIT, or I imagine anywhere else, which is highly stimulating, very collaborative, and come up with, I think, fairly meaningful results. The other thing that we've learned is that calorimetry is very difficult to do, and I think that's really been the main lesson for us. There are an awful lot of error sources, as everyone here has alluded to. So we're not, we're very careful to say that our results are for a low level of 9% level of confidence in the calorimetry, but we're fairly confident of our nuclear measurements. Thank you.
Let's take the first question. You, sir.
I see very striking difference. Young Kim and Purdue University. I see very striking difference between your experimental parameter as compared to Fleischmann, Pons, and approved by Texas A&M. That is the current used. You never used above 250 microamp per cubic square centimeter, yes. Whereas the other positive result by Pons, Fleischmann, Texas A&M used at least 600 milliamp. Is there any reason why you didn't want to use 600 milliamp?
No, there's no reason. At the beginning of these experiments, we decided we decided on an experimental design and a goal, and the goal was to, as closely as we could, mimic the Pons and Fleischmann data. And so we chose the middle power, or the middle current that they had, middle current density that they had suggested, which was 64 milliamps per square centimeter for showing excess heat. We know that our calorimetry is good to see the types of excess heat that they claim for that current density, and so we stuck with that. As our experiments proceed, we'll increase the power and see if we can see changes. But nevertheless, under the conditions that we've reported, and seeing no changes, Pons and Fleischmann and others have reported higher excess powers.
Let's take one more question here, sir. Your name, please.
Tom Schneider, the Electric Power Research Institute. You stated that you did not see any recombination. Is that correct?
I didn't state it, but actually our measurements, you know, again, we have an error bar. We say less than 5% recombination.
Less than 5% recombination. Yeah. Thank you very much.
Professor Bakris, yes.
I want to say a few words about this paper, but I think what I'm saying here applies to most of the papers with negative results. First of all, it's extremely important to compare with the electrochemical heat produced and not with the total energy input. Thus, the last paper, which before this paper, would come out to be a considerable excess over the electrochemical heat if you actually compared it not with the total electrical input, but with the electrochemical heat input, E minus 1.54, etc. Secondly, the first thing that Martin Fleischmann said to me when I called him up after the announcement was, you won't see anything under 4 to 6 millimeters. And if you take 4 to 6 millimeter rods, or 6 millimeter rods, you have to have a charging time of more than 72 days. So charging times alone will prevent attainment of those Pons-Fleischmann conditions at this time, because at the time of the phenomenon. Thirdly, in respect to the last paper, the choice of those current densities, if I remember the Pons-Fleischmann data well, I have it in my bag, but I haven't looked it up, would give you about 0.5 watts. 0.5 watts. And I'm not too sure that many calorimeters, except the Srinivasan type calorimeter, can detect that kind of thing. Now lastly, it is of course quite pointless to do a great number of experiments with very sophisticated nuclear detection apparatus of helium, tritium, etc., and find negative results if you haven't first of all shown that you are getting heat. There's some phenomenon, and goodness knows what it is. I daren't talk about being fusion, but it's something, which sometimes produces a heat. After you've got it, you might look for fusion products, and they might be there. But to look for them when you don't get the heat, well, something about shutting the door after the horse is gone, or something this time. The horse was never there.
Right. I have one here. Okay, well, I'd say, you know, the reason we look without heat is for completeness sake, because really no one here has presented fusion products at a level that could account for the types of excess heat that have been generated. In fact, most of the results are either excess heat or fusion products. The levels we've seen for neutron counting is something on the order of a billionth of a watt of excess power, clearly not detectable by calorimetry. So, you know, let's see, what was the other point, the first point that you made?
Well, the first point is, of course, you must use rods of 4 to 6.
Okay, the second to the last point, the first point for me.
You can't, at 250 microns, get sufficient heat to be seen on that.
Okay, in our apparatus, we've calibrated the apparatus with a resistor, and we can see changes of 10 to 15 milliwatts, and we're looking, as Professor Bakris correctly points out, we're looking for changes of 50 to 75 milliwatts. So the signal-to-noise ratio that we expect to see is something like 5 to 8. So we feel that we've calibrated our apparatus and can see the types of changes we're looking for.
Okay, I think we ought to go on to the next paper. And thank you so much for the discussion. The title of the next paper is In Search of Nuclear Fusion in Electrolyte Cells and Metal Gas Systems. And the authors are from Canada. They are D.R. McCracken, J. Paquette, R.E. Johnson, N.A. Bryden, W.G. Gross, A. Arena, A.M. Lone, D.C. Tennant, W.J.L. Byers from Chalk River Labs, Ontario, and the speaker will be Dr. J. Paquette.
Okay, is this mic on? Yes? Okay, the first thing to notice here is the multiple authors, and there's a good primary reason for that. The reason is that we can spread the blame more evenly if something goes wrong. The other thing to note is that the experiments were done in two different locations, at Chalk River in the province of Ontario and at Whiteshell in the province of Manitoba. For those of you who are not familiar with Canadian geography, Manitoba is in the western part of the country, while Ontario is in the eastern part of the country. And if you don't know where Canada is, see me after the talk. Can I get the next view graph, please? Beside geography, I will discuss some chemistry, and that mostly means the description of the electrolytic cells that we've used. Then I will proceed to discuss some physics, which is neutron detection. Then I will describe some of our results or lack thereof. The next view graph, please. The chemistry, the way we've tackled this problem is instead of working with one cell design, we've worked with we've worked with 11 cells total, and here I'm showing you the electrochemical cells. The first couple of cells were wire cathode cells. The dimensions are here. 7 meters of high purity wire was coiled around a ceramic cylinder. Surface area, the mass of the cells, the current density, and for how long this current density was applied. You can't hear me, yeah? Is that the problem? Okay, I'll try to use this one then. Is that better now? Okay, so current densities were reasonably low, actually, in the area from 50 to 100 odd milliamp per square centimeter, and the electrolysis in some cases lasted for 26 days up to 45 days. The next view graph. The next view graph shows you some of the chemical parameters for the cells that we've used, and for comparison I have put some of the same parameters for Fleischmann and Pons and Jones and al. Cells. Okay, here in the case of the Brigham Young University cells, the electrolyte was various salts and nitric acid. Volume was reasonably low, 20 cc. We don't know if any form of chemical analysis of the electrode was done before or after. We don't know what the temperature was. And surface preparation, which is generally all important in electrochemistry, the electrodes were cleaned with dilute acid and abraded sometimes. That's from Jones' paper. We don't know much from Fleischmann and Pons' paper except for the electrolyte, which was 0.1 molar LiOH, and we don't know any of the other parameters. Our electrode, the wire electrode, we use 0.1 molar LiOH to try to duplicate Fleischmann and Pons conditions. The cells had rather large volumes. We used what was available at the time, and the wire was high purity, 99.995% obtained from Johnson Matthey. The cells were run at ambient temperature, and there was no surface preparation of any kind of shape done. The sheet electrode is a large sheet electrode. Again, same electrolyte, same cell. It was analyzed by dissolution followed by atomic absorption analysis, and the material was contaminated with silver, common contaminant in palladium, at a level of 0.13 atom percent, and no surface preparation was used on that particular electrode. Next view graph. We just keep moving down the list. We had the large rod electrode in cell 2, same electrolyte, same volume. It was made from the sheet material described previously, so the major impurity or contaminant was 0.13%. silver in the cell. And if we can just move the view graph to the side a little bit, the electrode was made by fusing the sheet material, and casting was cold work, annealed at high temperature, washed with acetone, aqua regia was used, then it was washed with water and abraded, quite an extensive list here. The next rod was made from a high purity palladium sponge obtained from the National Research Council in Ottawa in Canada, and it was analyzed by DC arc spectroscopy. It was found to have 10 ppm of silver as an impurity. That's quite low for palladium. The surface was analyzed using XPS. There was no detectable impurities. The electrode was made in the same way as the previous one, that is fusing, casting, cold working, was annealed, and the difference here was that this one was electropolished in methanol. The next one, the cell volume was smaller. It was made from the same high purity palladium material as the previous electrode, and it was subjected to the same treatment. We then started to change the electrolyte to LiOD for the next electrode, which was a rod electrode. We purged the cell with deuterium gas. The cell had a volume of about 55 mil. The material was palladium 99.995%, which was obtained from Johnson Matthey and was not analyzed. It ran at close to ambient temperature. Those cells were jacketed and were water cooled, and it was cleaned with alcohol before use. We've used also tube electrode. This particular cell at the bottom was a commercial water electrolysis unit that has been in use at the ECL for many, many years to produce deuterium gas from D2O. The material is a silver palladium alloy, 3% atom silver, and it was not subjected to any form of a surface treatment. Next. And we keep moving down the list. We've used various tube electrodes. We've changed the electrolyte to acid solutions as opposed to basic, using deuterated phosphoric acid in a couple of cases. And finally, we've used a large rod. The chemical analysis on that one is in progress. Okay, if we move to the next view graph. Now that you're thoroughly confused with all the electrochemical and chemical parameters, I'll show you a summary. We've used palladium cathode exclusively, platinum counter electrodes, current density from 20 to 140, a little bit on the low side. Electrolysis time from 0.5 to 28 days. There's one case at 45 days. The cathode masses range from 2 to 41 grams. Surface areas from 3 to 140 square centimeter. Geometries, wires, sheet, rods, and tubes. The cathode chemistry from 3% silver to high purity palladium, and various surface preparations were used. The next view graph. The electrolyte was varied between 0.1 molar lithium hydroxide, lithium deuteroxide, and deuterated phosphoric acid, and the temperature was controlled between 16 and 50 degrees C. So I would like to be able to tell you that that was all done neatly and systematically, but that was not the case. A lot of what you see there is the result of a continuously evolving design. The next view graph will show you a generic cell of the type that we used. The cell in this case has a palladium rod cathode. A platinum foil surrounds the cell. We use a Teflon spacer to get even spacing and get uniform current density on the surface of the cathode. And the cell is jacketed and water cooled. And an interesting feature of the cell is that we use a wet-proof catalyst that was developed years ago by AECL to recombine the evolved deuterium and oxygen. And this has many advantages. The recombination is 100% efficient. That way we don't have to worry about this tritium deuterium electrolytic separation business, and it offers some advantages for calorimetry, as we will see later on. The next slide shows you how we compare with Fleischmann and Pons as for the various electrochemical and chemical parameters. I have plotted the excess power that's extracted from table 1 in their paper, and I have plotted that assuming that we have a bulk effect against the current density times the mass of the electrode. Okay, this is the resulting curve. The black dots are the data from Fleischmann and Pons table, and on the top, the arrows represents the conditions that we've explored in our experiments. Okay, and there's one extra data point at 3,000 odd there. So we bracket the conditions that were used by Fleischmann and Pons. Now, what is reported in their paper is that for this condition of current density and mass, tritium is detected at 1.7 becquerel per cc, very low indeed. And for this particular condition here, a neutron flux of 4 times 10 to the 4th is reported to have occurred in the cell. The next view graph show you the same data plotted as function of current. It is assuming that we have a surface effect as opposed to a bulk effect. And again, the black dots are the data points from Fleischmann and Pons table, and the arrows across the top, those are the conditions that we have used in our experiments, and there's a whole bunch of more data points far to the right over there. So we feel confident that we've bracketed those conditions reasonably well with our cells. The next view graph, we've also attempted to duplicate the experiment by the Frascati group in Italy by varying the temperature and the pressure over a titanium deuterium gas system. We've used a 100 gram of titanium sponge material. On the left-hand side is the temperature scale corresponding to the full line, and on the right-hand side is the pressure scale corresponding to the dashed line. So the experiment consists in heating the titanium material to 600 degrees under vacuum, then applying a pressure of deuterium gas as the material is cooled, the pressure being 40 atmosphere. Then the temperature is dropped to liquid nitrogen temperature, the system is pumped down and allowed to drift back to room temperature, and we've attempted to measure the neutron flux all along. That's one typical curve. We've done more than one experiment of that type. The next view graph. The next view graph now, we're moving into the physics part as opposed to the chemistry. And what we see here is a list of the neutron detectors that we've used in those experiments. They are all conventional moderated detectors, mostly helium-3 based. There was one BF3 based detector. I've given them neat little tags here, CRNL1. Those are all detectors at Chalk River, and the 2 other ones are detectors at Whiteshell. They shielded with wax and cadmium, in some cases with polyethylene and polypropylene. The moderator is wax for the Chalk River detectors, polyethylene and polypropylene for the Whiteshell detectors. They range from 1 helium-3 detector to 5 helium-3 detector, 1 BF3, a ring of 8 or 7 helium-3 detectors in some cases. And the detector that was most extensively used in our studies is CRNL3, consisting of 5 helium-3 detector. The efficiency of this particular detector was determined using plut beryllium, plut lithium, and californium-252 sources in both heavy water and light water, using tubes of exactly the same dimensions as the electrochemical cells. The efficiency of the other detectors were estimated from the calibration of this one, since the same helium-3 detectors were used. And the ones at Whiteshell, the efficiency was estimated. The BF3 detector was calibrated, the efficiency was determined using a plut beryllium source. Background, they all have fairly low background. The units here are 10⁻³ per second. The detector that was the most extensively used has a background of 8.3 plus or minus 1.5 10⁻³ second minus 1. That corresponds to about 30 counts per hour as background. The next view graph shows you a top view of detector CRNL3, the one that was the most extensively used. It consists of a large wax shielding, roughly 1.3 meter. Canada is a metric country, by 1.2 meters. In the center is the cell with the palladium cathode. There's a D2O, of course, in the cell. There's an air gap, an aluminum can. There's the 5 helium-3 detector. 2 were 1-inch OD, and 3 were 1/4-inch detectors. wax moderator and cadmium shield. The next view graph shows you a side view of the same detector with the cell in place, close to 1 meter tall. That's the wax shielding all around. We see the cadmium shielding, aluminum cam with the cell, the palladium rod in the center, and that's the wet-proof catalyst to recombine the evolved D2 and oxygen. Wax moderator and 2 of the large helium-3 detectors. The next view graph gives you raw data for the efficiency determination for detector CRNL3 with the 3 sources, the Plut lithium, californium, and Plut beryllium sources. The source strengths are on the bottom here. Those are the raw counts for the 5 detectors, the total, and if we can move the view graph a little bit here, we see the efficiency for the various sources. All this is as you would expect, going from Plut BE to Plut lithium and D2O and light water. 1 minute, okay. So we conservatively estimate that the efficiency is about 1.6 plus or minus 0.8%. And the next view graph shows you the test matrix, what cell was in what detector for how long. So those are the total electrolysis times for the various cells, the current density, the time spent in the various detectors, and this one was the most extensively used detector. Next one. Results for cell 4 and 5 over nearly 500 hours. We've switched cell at 200 hours here, and what we get is background. This is not any different from the background counts. The next view graph shows you the statistics. That's a Poisson distribution for the data I've just shown you with the fitted curve. The chi-squares are good. So what we have is a good measurement of the background over 500 hours with those 2 cells. The next view graph is a summary of the neutron detection. Fleischmann and Pons Bond-sphere detector, that's the flux that they have. That's the fusion rate that they have, assuming PDD 0.7. Jones, with his detector, much lower neutron flux, much lower fusion rate. The Italian group at Frascati with a gas phase system, fairly high neutron flux, reasonably high fusion rate. Our attempts at looking at that gas phase system, we can put an upper limit of 4 times 10 to the minus 25 on the neutron flux, much lower than what was observed in Frascati, and fusion rate for the various, upper limit of fusion rate for the various detectors that we've used, all quite low. We would see the kind of neutron flux that's being reported by Fleischmann and Pons, but note carefully that we're not quite sensitive enough to really verify Jones and all experiment. We can't reach that kind of low level by a factor of about 2 or 3. Those are all given for 1 hour counting time, 3 sigma statistics. The next view graph, more detectors. Those ones are less sensitive. The background is higher, so the limit to the fusion rate is much higher. The next one. I'll just go quickly through some preliminary calorimetry. We have a calorimetric system which is very, very similar to the one that was described by the Oak Ridge group a couple of talks ago. We have a constant flow of water at controlled temperature coming from a water bath. We use a balance to measure accurately the flow rate. The cell is inside the insulated calorimeter. The next view graph shows you the internals. This is the cell. This is the cooling coils bringing the water from the water bath. So we have a constant heat leak here on that system. And the next view graph will show you the cell. The cell is completely submerged in the calorimeter. It is supposedly waterproof. It has flooded a couple of times with light water. And we have the wet-proof catalyst, so we don't have to subtract the 1.53 or 1.54. We don't have to worry about recombination. We have 100% recombination in that case. And the results, preliminary results for a couple of experiments with cell 2, current density 100 milliamp per square centimeter, 5 watts. Power out is power in, plus or minus 0.1 watt. No excess heat. However, we are not sensitive enough to detect the kind of heat that was reported early this morning by Texas A&M. And if we can go to the conclusion view graphs, it's 3 or 4 view graphs down. I will skip the tritium results. The results are non-conclusive. That is, within our limit, we don't see any massive excess of tritium accumulating in our cell. And conclusion, we do not observe the neutron flux reported by Fleischmann and Pon. We are much more sensitive than they were. We are, however, not sensitive enough to confirm the findings of Jones and al. We feel that more detailed calorimetry is needed. Some self-criticism here. Maybe not enough time. Maybe the electrodes are too small. Maybe we've got the wrong surface on those electrodes. Maybe the current densities is too low, and you can go on and on. Thank you.
Yes, sir.
Young Kim, Purdue University. I think you are using too low current. There is a conventional nuclear physics explanation which will be in the poster, where it's very critical to use a high current to create plasmas around ion plasmas around the PD cathode. If you want to find out explanation, you can come to.
Okay, well, my answer to that is, have you had any success with your experiments?
Well, this is first time I'm presenting poster, so everyone can find out what it is and then try to do experiment.
Yes, I will take a close look at your poster. My point is that we don't know what are the parameters that will make this experiment work or not work. So you could see in the self-criticism there that yes, maybe the current density is too low, maybe other factors are important.
Let's go with here.
Stan Lockhart, MIT Plasma Fusion Center. So far in all the experiments reporting excess heat, that excess is really no more than the chemical power evolved in producing D2 and O2. And it seems like your method of calorimetry, where the recombination is done in the cell, is the correct way to go. And so my question then is, why is the error bar quite so large as it is, 100 milliwatts? It seems like this is the right approach, though, because
right. Yeah, the recombiner we feel is the right approach. Now, the large plus or minus comes from the design of the calorimeter. That is not an optimum design. It was designed to look for a large amount of heat on a sustained basis. It was not designed to look at microwatts or milliwatts for short periods of time. So, this design will evolve. We're in the early stage of the calorimetry game, obviously.
What's the detectable watts per cubic centimeter?
Oh boy, I can't answer that. The electrode was quite large. It was a 40-gram palladium cathode that was used in that particular experiment.
Professor Guy.
Why don't you know? You had two data points that showed the fusion rate at the level of 10⁻25 and 10⁻24. But then you say that you don't have the sensitivity. But then you say that you don't have the sensitivity to check the result of Jones.
That's correct. The 10⁻25 was for the gas phase system. Okay, it was not for the electrolytic cell, and it is that low because we have 100 grams of material. The 10 to the minus 24 result was for, again, a very large cathode. Okay, so this number factors in the mass. Okay, so obviously the larger the mass, the more sensitive you are.
How much larger is the mass?
In one case, the titanium gas system, we have 100 grams. The 10⁻24 was for the 40-odd grams electrodes, and most of the other ones are between 3 and 15 grams.
Maybe one more question. Yes, sir, here.
Hanson, Westinghouse R&D. In the Frascati type experiment, did you see any evidence that the deuterium reacted with the titanium?
In what sense?
Was there a decrease in the deuterium pressure when you added it to the titanium?
Well, we didn't monitor the pressure that closely. We applied 40 atmosphere. of deuterium on it, so we wouldn't detect half an atmosphere pressure decrease or something like that.
Did you see any evidence, did you take a look at the titanium after the reaction?
We didn't analyze the titanium after the reaction.
One more, all right?
Norm Goldstein, Westinghouse R&D. Did you make any effort to determine the amount of deuterium you got into the palladium electrode?
Yes, we did. That's I ran out of time on those. Yes, we use surface analysis techniques, SIMS, secondary ion mass spectroscopy, to sputter the surface using oxygen and cesium beams. And what we found is that you have a small excess on the surface, which comes from surface roughness and presumably absorbed D2O. But after that, as you go down, the composition remained, the palladium over deuterium ratio remained constant down to 20 microns inside the electrode. Okay, that doesn't tell you the absolute V over PD. It remains constant. Then we did bulk analysis by thermal desorption of deuterium from our electrodes after 28 days of electrolysis, and the composition was PDD 0.72.
All right, that's always the critical parameter, and there's a lot of discussion that you need a value of around 1 to achieve positive results, but that's one of those debatable points.
That's right. However, there's no way of knowing in our experiments if we've lost some deuterium in transferring the electrode from the cell to the thermal desorption apparatus.
Thank you very much. Before we break to see the poster presentations, I'd like to give about a minute to Dr. Bakris, who is the discussion leader of the evening section.
Well, the general idea of this evening session is to break it into 2 parts. The first part, lasting about 1 hour, up to 1 hour, we've been given to a series of short presentations from people who feel they have definite results to contribute which have not been included in the program. Now, about 6 or 7 people have approached me already, but I would ask anybody who feels they have something which is appropriate, something where they can come and say it all in 5 or 6 minutes and get a couple of questions in a definite way, come and see me in the next half hour. We'll put all those names down, and finally I'll have to choose 6 people. Now, that's going to take about an hour. After that, it's free, and say what you like and discuss what you like. I'll take questions from the floor, and Dr. Jensen has said the session doesn't have to close at the end of the 2 hours. So we'll just go on as long as it takes. Thank you.
Very good point. But we do want to start again this afternoon at 1:30, so we'll see you then.
Yes. No audio. Yeah, I do. No, it's thinking of 100.
No. TNT Bell Labs. The paper is going to be presented by Dr. Broer. The title that's on my form sheet here says, "A Search for Neutrons from Cold Fusion in PhDs." I think that means palladium deuterium, but there may be a lot of PhDs involved. Dr. Broer, please.
Yes, there are indeed lots of neutrons in... Okay, is this better? I'm having problems with my slides here also. Okay, the work that I will describe concentrates on the detection of any possible neutrons coming out of a PDD system. My main collaborators are Raju Raghavan, Len Feldman, Joe Kraus, Anthony James, and Don Murphy, and this was done at the research division of AT&T Bell Labs. What we have done is concentrated in the first 4 weeks of the experiment trying to reproduce the Pons-Fleischmann results and focusing in on palladium materials only at this point in time. We have used typically palladium wires in the order of a little over 1 millimeter diameter by about 9 centimeters long. One of these wires was cold drawn only, the other one was cold drawn and annealed. And the larger rod, which we've used also, which we cast ourselves in boron nitride crucibles, was subsequently cold drawn to reduce its diameter, and hence after that annealed around 900 degrees centigrade for 1 hour in nitrogen. The cells are fairly conventional, 99.5 D in heavy water, 10 to the molar lithium OD, platinum anode wire cage. No deuterium oxygen recombination was allowed, and a modest current density of about 50 to 60 milliamp per square centimeter. For the detection of the neutrons, we relied mainly on a roughly 5-inch cube sodium iodide detector system, which is shown schematically here. 5-inch length, 5-inch diameter, with a PMT behind it, the cell sitting in front of about 2 inches polyethylene. This whole thing is surrounded by typically 4 inches of polyethylene all the way around it. 2 veto plastics, both above and below it, were used to do an anti-coincidence setup to essentially veto all cosmic rays, muons. The whole thing was surrounded with lead to take care of the significant amount of mainly radon-induced gammas. As you well know, New Jersey has the questionable honor of having one of the highest radon concentrations in the world at this point in time, and hence we were very worried about that. Lots of borax around it to shield against spurious neutrons. Now, what I want to show you is something that not many people show you, is an actual spectrum from this thing. And the reason I'll do that is to introduce something here which we did, which I don't think anybody else has done in terms of the actual use of the sodium iodide. Here's the well-known spectrum of the sodium iodide. There's some lines clearly recognizable here. The potassium-40, there's a slew of uranium lines and the daughters. Notice the region of interest. The 2.2 thereabouts MeV has at least three uranium daughter lines. Needless to say, that can cause great confusion in terms of interpreting that due to the NP-gamma reaction. This spectral region I'll call region R2 for the moment. What we have realized is, though, that you actually are better off if you rely on the interaction of thermal neutrons with the sodium-23 and the iodine-128 inside the sodium iodide detector itself. And this causes gamma photons at the energies well above 3 MeV. And this is shown here in this region R1, where there's very little background due to radioactivity. And what you will see later on is that will greatly enhance our detectability in terms of and hence the limits that we set on neutron production. What I've shown on the top here is just the spectrum that you get when we calibrate our system with an americium beryllium source. You see well-defined lines, of course, the NP-gamma there. Here's this broad spectrum underneath here. These are all different gamma energies due to the interaction of the slow neutrons, the moderated neutrons, that is, with the sodium-23 and the iodide-127. To just demonstrate that, schematically shown here. Here, this shows the three essential neutron detection modes. The slow neutron activates the sodium-23, brings it up into an excited state of about 6 MeV, which gives you a whole variety of gamma energies. The same thing is true with the iodine. Now, I've drawn 3 photons here. This is really representative of a very large amount of different energies, and just to throw this up here to convince you of that. This is iodine-128. You see there are many, many of them. Well, at very high energy, this is around 7 MeV in the first excited isospin state. And of course, at the bottom is the conventional one, is the PD gamma reaction. But again, this is nice because at these higher energies, 6 to 7 MeV in that region, It's just much cleaner to do. There's no confusion with natural radioactivity. Let me throw this up here, show you this show you what can go wrong. If you don't look at the higher energies, if you look at 2.2 MeV, this region R1, how incredibly sensitive it is to natural radioactivity. Here we moved around a couple of polyethylene blocks, and it makes a tremendous difference. Obviously the shielding got messed up a little bit, and you see this enhancement in the counting rate. Now the data I'll show you are essentially that of the 4mm rod towards the latter part of the 4-week or thereabouts time period that we run these samples. What I show you here is the count rate versus days after start. After about 14 days or so, we discontinued the 2 wires. We essentially blew them up intentionally. This is what I mean with we had 2 cells running here. At that time we blew them up. We degassed them by applying very high currents very rapidly and see whether you get any bursts of neutrons out that way. Essentially, nothing is happening there above background. Then the average level shifts a little bit due to the distribution of the shielding. The solid angles change somewhat. And from then on, we have only the 1 cell in place with a 4mm rod. So here, a single live cell, and the shielding is now undisturbed for the remaining part of the time. Towards the very end, we turned the cell off, the large rod as well. We removed it, and we inserted a blank cell as close to the original cell as possible, filled, of course, same glass and the same concentration of lithium hydroxide and so forth. Interesting to note on this scale is this corresponds roughly to 1 neutrons per second. So that tells you already roughly in what regime we're working in here. In terms of the upper limits, because this essentially is a 0 result, of course, is that the signal is in the order of 0.14 plus or minus 0.0004 per second. The background is about essentially the same with somewhat larger error bar because we have counted less time during the background measurement. So the observed effect is to first order the sum of these 2 uncertainties. The efficiency, which was determined from the calibration with the americium beryllium source in situ, that is in the water with lithium hydroxide around and so forth, was about 1.5%. We deduce a neutron signal of less than 1/10 of neutron per second for this 4mm rod, which corresponds roughly to 0.01 neutrons per second, less than 0.01 neutrons per second per gram of palladium. And just to compare this and put this in perspective, Pons Fleischmann, as you well know at this point in time, claimed originally to see on the order of 10 to the 3rd neutrons per second per gram palladium, so we're at least 5 orders of magnitude below that. The fusion rate, which we derive from this number, is in the order of 2.2 times 10 to the minus 24 ddn. This is the deuteron plus deuteron gives you neutron and helium-3 fusions per dd pair per second. And to make the comparison here, and this will be my last comment, is Jones et al. In their experiments claimed in the order of 10 to the minus 23 ddn fusions per dd per second. But this is really, from what I've learned from after talking to Steve Jones, at peak value, and their average rate is typically 10 to the minus 24, so we're pretty close to that, which is not unreasonable, within factors of 2 or so. But needless to say, we're well below what Pons Fleischmann have claimed to have seen. That's all I have to tell you. Thank you very much.
Any discussion?
Yes.
Moshe Guy from Yale. We tried to do the same thing that you did, and we found that you have to know very carefully the line shape of the gamma rays in your detector to get a meaningful upper limit. Because basically what you're doing is you're summing on a cascade, which is all inside the detector, plus the beta, and the line shape of this sum up. Did you study this very carefully? This will change your upper limit by some factor, the exact knowledge of the line shape. Did you measure it and study
No, we did.
it?
If I understand you correctly, I assume you're talking about the line shape of the gamma's energy above, say, 3 MeV?
Well, basically you have an edge at 7 MeV,
Right.
which will produce a shoulder going all the way to low energy, because
That's
you
right.
sum up many gamma rays in the cascade. In the
That's
case of
right.
iodine, in the case of sodium-24, you sum up basically 4 gamma rays, and then on top of that you also have the beta, which all occur in the detector. And that gives you a very, very unusual line shape that you have to study very carefully.
No, we have not done that. The cutoff was around a little below 7 MeV.
So I should like to remark that if you will study this line shape very carefully, that in fact will reduce your upper limit.
Okay.
We have done that.
Even further than...
Further down.
Okay, thank you very much.
Any other questions for Dr. Broer?
Yes, over there. I can't hear you, I'm sorry.
Please state your name and...
Henry Randolph, Savannah River. Did you measure your loading on the palladium?
I'm sorry?
Your deuterium loading on palladium?
The loading on the palladium. No, we have not measured that quantitatively. No, we have done, prior to, when we first started this, the first experiment that we did on some wires, the D2O was contaminated with H2O by small amounts, but we stopped the experiment after a couple of days. These are very small wires, like less than a millimeter diameter. And the weight increase at that point in time, even though it was contaminated with regular water, is a small fraction. Corresponds to the other order of 0.7 to 0.8. But we have not measured very carefully the loading of the, particularly of the 4 millimeter rod after this is over. All I can say to you is a very qualitative thing, that the thing was outgassing like mad, but that's not a good enough answer, obviously.
We have time for another question.
Okay, thank you.
Is this mic live? Thank you. I'd like to call for the second paper this afternoon, Calorimetry, Neutron Flux, Gamma Flux, and Tritium Yield from Electrochemically Charged Palladium in D2O. Lewis, Barnes, and a host of people whose names do not appear on the program. Dr. Lewis.
I would like to tell you about the work that's been done in cold fusion at Caltech. There are a number of people that have been working on this. People in my research group in chemistry. They include electrochemists and people with some expertise in hydrides, people in chemical biology that know something about tritium counting, our chairman of the session, Charlie Barnes, and I'll refer all experimental nuclear physics questions to him. I've learned a tremendous amount. Steve Koonin as well for theory. We've had some remelted palladium with geologists, and people at the NSF mass spectral facility in UC Riverside have helped us try to detect helium. We've looked for 5 characteristic features. Neutrons at a level roughly of 1/10 of a neutron per second on average. I'll be more specific a little later. Gamma rays from 20 keV to 30 MeV. Tritium at the level of the natural background of tritium in D2O, at least in our commercial D2O. Helium at the resolution of our mass spectrometer. It's actually better than that. We're at a couple tenths of a part per million in the gas headspace, not in the rods. And heat, calorimetry in a system very similar to that used in A&M, but by a method very similar to that used at MIT. And we have pretty good error bars to within 6%. I'll take the experiments in that order. There's the neutron cube. We detect thermalized neutrons in 12 helium-3 proportional counters. The efficiency is between 20 and 24% when all 12 counters are in operation. For some runs, as few as 8 were in operation for an efficiency of 14%. The background rate was between 75 and 85 counts per hour. And there was appropriate shielding. We could also veto cosmic rays and muons. We also looked for statistical correlations between muon coincidences with neutron decays and never found any. Here's an example over some calendar days of several foreground and background runs interspersed. The cells were started much earlier than this. They were running for several hundred hours. We'd put in a cell. I'll tell you more details about the palladium in a little bit, but this just gives you an idea of the ratio of the foreground to the background, and you can see that within our statistical significance, except perhaps for this one point, in this period of time, we never saw anything above the background level. We've done more neutron experiments than that. I just want you to get out of this table some of the conditions that we've used. We've used commercially available very small diameter wires that should activate relatively quickly. We've not activated them. We have annealed them. We've used cylinders. We've used samples given to us by Chuck Martin at Texas A&M and annealed that. We've also pulsed the electrolysis. We've used 0.22 centimeter diameter rod that's been annealed. We've recast some palladium rod. We've recast it in alumina. We've also recast some by centrifugal casting. We've annealed them in some cases and in others not annealed them. Here are the activation times that you would predict based on those diameter rods. The bold numbers are the longest times that we've analyzed neutrons. The cells are always maintained charging. They're put in the neutron cube, analyzed for a run typically 10 hours in duration, then moved over to a set of gamma ray detectors that I'll talk about later on. For instance, this cell should have activated in 6.9 hours. Between 559 and 570 hours after its run, we saw no statistical significance for neutrons, and the other bold numbers tell you up to 43 hours of activation for this cell. We ran for 277 to 291 and saw nothing. As the diameter and volume, therefore, of the rods gets larger, we can place better limits on the specific neutron flux in terms of these units of neutrons per hour per cubic centimeter of palladium. In these units, the Utah results, University of Utah, would be on the order of 10 to the 8th neutrons per hour per cubic centimeter palladium. Our 2 sigma uncertainty is on the order of 10 to 100 neutrons per cubic centimeter per hour of palladium. We've also then looked at gamma rays produced. We've looked from 20 keV to 30 MeV, both with a high-resolution germanium detector and with a large 15 by 15 by 15 sodium iodide scintillation counter to look out at the 23.8 MeV gamma rays. And again, you see we've run for very long periods of time compared to the activation. We've never seen anything statistically significant, and I'll show you that data also. Here's a foreground spectrum of one of those cells after 12 days. This is just in the region up to 6 MeV. I'll overlay the background spectrum. You can see there's no difference. The sensitivity of this would be about 100 fusions per hour, at least at the 5.5 MeV line, and a couple hundred neutrons per hour out at the 23.8 MeV line. I also note we saw no Coulomb excitation or Bremsstrahlung or annihilation peaks that you might expect from some of the potential fusion reactions on these cells. And this was typical of all of the cells that we ran. We never saw anything statistically significant above background. Tritium. We've done some tritium analysis on almost all cells. This is a typical result. These are the decays per minute. This is what we would get just in the water that we use as the feed. This is for commercial D2O, which has typically 10 to the 9th tritiums per cubic centimeter of D2O. After 458 hours on a particular rod that was held at 64 milliamps per centimeter squared, we had a very small increase compared to just the water itself, and we can account for all of that within the natural separation isotopic factor of D compared to T. And we could place an upper limit for these particular experiments of on the order of 10 to the 3rd tritiums per cubic centimeter per palladium, as opposed to the number reported in Utah. I'd like to point out a potential difference between these cells and the ones we saw with large levels of tritium at Texas A&M. As I understand it, those anodes were nickel. Our anodes are platinum. Potentially the nickel dissolving in the solution might make a difference. It's something that we'll look into. We also looked for helium in the headspace. We wanted to see whether or not we could resolve helium in the presence of air. We looked on what we believe to be an identical model mass spectrometer to what was used in the University of Utah studies. We were able to see helium at its appropriate mass to charge ratio in air. Relative to argon peak, the ambient air had 4 parts per million plus or minus 1 part per million helium. when we eliminated helium from the cells, that is, when we eliminated air from the cells, as evidenced by the fact that we saw no argon peaks and no nitrogen peaks in this region of the mass spec, we saw no helium in the headspace to our detectability limit, and that's a couple tenths of a part per million. Another thing that's interesting is that this instrument is a magnetic sector machine. If you just tune on a peak out here or to tune on D2, a peak of helium will potentially go out of focus. You have to optimize each peak independently, or these ratios can be arbitrarily large or small. So you could find a lot of helium relative to D2 or a little bit, depending on whether or not the machine is tuned to each peak. When we tune it optimal focus, this is done by the people at the NSF Mass Spec Center, and they find no helium in the headspace of a cell that was a 0.2 centimeter diameter rod run at 64 milliamps per centimeter squared for several weeks. It was typical of several of the cells we looked at. Calorimetry, we've done many calorimetry runs. This is a not to scale schematic of our system. We have a constant temperature bath, a 60-liter constant temperature bath maintained by active feedback to a millikelvin. It's a Tronat calorimeter, very similar to the model used at A&M. We don't, however, use it in the constant cooling heating mode most of the time. We use the same method generally as the MIT people have used, where you put a given power through the electrolytic circuit. You have a power that's also gone on through a calibrated load resistor to maintain a constant temperature of the system relative to the bath. We then either increase or decrease the power through the electrolytic circuit, and then determine how much decrease or increase in the load resistor we need to maintain a constant temperature. The ratio of this power to this power then will tell us if any excess power is created this way. Of course, we should be evolving fuel. The correction for this voltage is 1.54 volts. And so actually we should, if we're evolving this gas, have to apply less power here to compensate for an input power here in the absence of any excess power production by the circuit. And we stir very well to maintain a uniform temperature profile. We vary this and measure with several different thermistors at different places to ensure that. Here's data for a particular set of runs. The only thing you really have to concentrate on here is that we'll decrease the power in the cell by 0.283 watts. To maintain the same temperature, we have to increase the resistor power by 0.212 watts. Or we'll increase the power in the cell and decrease the power in the resistor. We always have to vary the resistor less than the power through the electrolytic cell. That's in accord with what you would expect if you were losing some of the input power in terms of the fuel. We can correct for that. When we do that, here's the predicted number. We should only have to have 0.208 watts produced. We measure 0.212, and so we're in excellent agreement for this particular set of runs. That is, we had no evidence over this particular 161-hour run on this cast rod for any excess power production, and this was typical of almost all the experiments that we've run. And I'll tell you why I said almost all in a little bit. If we calculate how much excess we would have based on that corrected value, we'd have at most 6% excess, and that could clearly be consistent with a small amount of recombination of the gases, which would deposit some of that power back into the cell, and that makes reasonable sense. Those are our data as of this time. One thing that we've noted is that in this experiment, in the Dewar, when you apply a given power and you measure the temperature, you have to do a continuous calibration of the rate of heat loss. Otherwise, the temperature can rise, and you'll think that you have extra power produced when in fact it might alternatively be that the rate of heat loss has changed. And the heat loss in the system depends on the rate of bubble evolution. That changes with time. When you're charging the palladium versus when you're actually evolving gases, that also changes with time. This is an experiment for a particular cell which just shows you the degrees per watt that we measured as a function of time. And you could see that if you calibrated down here, by this time you would see you would have excess power produced based on this calibration point. If you recalibrate out here, we don't see any power production. An important feature to check is that if you see an event that you think is excess power, you have to ensure that it's not just a decrease in the rate of heat loss to maintain a higher temperature. And so we recalibrate all the time whenever we think we see a glitch in the temperature rise. We've never seen any evidence after the temperature rise for anything other than a change in the heat loss constant. I've also been told by many people that I should present the raw data of the Utah results. We've worked backwards to do that. I just want to give you a feeling for the magnitude of the numbers. We could easily measure those numbers in our calorimeter, at least at the medium current densities and the high ones, but I want to give you a feeling for what the numbers really were as reported in that paper, since the table is not particularly illuminating on that fact. For instance, on the highest current density on a 10th centimeter diameter rod, 15.5 watts were put in. The measured value, if no gases would recombine, is expected to be 13.1. The actual reported measured value was 13.7. That's still less power than put in. We assume all the gases have escaped and none have recombined, and it's that difference of 0.654 watts that is called the excess power generation by this rod. And so this is the accuracy with which you need to measure this input power to determine if, in fact, these rods are actually evolving any excess power. And you can see that here we're talking about 3 excess watts out of 26 in. Only number down here, which is very large, 26 out of 55, was a scaled number. We don't actually know precisely how that was scaled and what the raw data was in that case. That's interesting to think about. Several people have also wanted me to explain the formulas used as best we know to calculate that table. I'll do that also. This first set of numbers was the excess power produced by the cell as measured in the calorimetry. And then subtracted from that is the power you would have expected to be deposited into the cell if all the gases would have escaped. That'll be less than the total input power. It's corrected by the 1.54 volt correction for water electrolysis in D2O. Note it's somewhat different in H2O. It's only 1.48. You have to take that into account in comparing differential measurements in D2O and H2O. And then this numerator, the excess over what you thought you should have if all the gases escaped, is divided by 3 separate quantities to get this column. The first quantity is by that amount that you thought you deposited in terms of joule heating. And that's the numerator and denominator here. In the second column, we keep the same numerator, and we're going to divide by the total input power, which of course is always greater than just the amount that went into heating the cell. And so these numbers are correspondingly smaller. And the third column is dividing this numerator not by the actual measured cell voltages, but by assuming that we could get this same excess power if all we did is put in half a volt and fix that number at half a volt, as opposed to the actual measured numbers. And so you should interpret these 4-to-1 and 10-to-1 power out to power in ratios with that caveat, that it's not a measured number. And I think it's reasonably well documented that it's very difficult, if not, we've never been able to observe half a volt and depolarize the anode to that value, and there are good reasons from the first law of thermodynamics why that might be the case. I'll finish up with a couple facts that I think are useful. One, as the people just raised, I think it would be very useful if people reported their deuterium to palladium stoichiometries. We've done this for 3 different rods that have been charging for between 2 and 3 weeks at 64 million per centimeter squared. The method is very easy. It was suggested to us by Dan Lockhart at MIT. You simply pull out your palladium rod and then deposit it into a tube. The tube contains argon that's in there so that when you evolve the hydrogen, you don't recombine it with oxygen and explode yourself. And you displace water. And you can displace 100 cubic centimeters of water out of one of these reasonably small diameter rods and measure that very accurately, and then analyze the gases and make sure that they're deuterium. You can take a Bunsen burner to accelerate the process, or a propane torch, just heat up the palladium, it all comes out in 15 minutes, and you have a very easy method of analyzing the stoichiometry. I'll also point out that if you don't take care to charge the rods, it's easy to get surface active impurities, that if you just flip the switch, rods will evolve gas and never charge. And so I think it's important for people to establish it might be the case that we need to go higher in stoichiometry than this, deuterium to palladium. We haven't done that. Okay? I've got 1 minute? Good. Hydrogen content in D2O. If you just leave D2O out in air, then it will exchange protons with H2O. It's important to seal it up. I think it's also important for the community to know what the levels are so that perhaps that's a discrepancy. In one of our cells after 3 weeks, you can do this by NMR techniques. Ask the chemist friend to run a spectrum relative to benzoic acid as a standard. Our cells after 3 weeks were only 0.8 mole percent H2O compared to D2O. Third things which are interesting to note and also would be useful to compare is what are the actual charging potentials of the cathodes. Our cathodes we measured while they were passing current were at -1.6 volts versus a palladium alpha beta phase reference electrode. We can correct that for the electrical resistance of the solution, which is known independently. They were at -1 volt. We can also interrupt the current and read the open circuit potential. That corrects for chemical resistances while it's charging, which this does not. This is just the electrical resistance, and that's -0.7 volts. That's consistent with the value of -0.8 volts reported by the Utah people for the electrochemical potential of the palladium charged phase. But I think there might be differences among different groups, some who have seen the effects and some who might not. It'd be very interesting to know the content of the deuterium and the palladium, the content of the H in the D2O, and these potentials for those particular samples. Finally, to summarize our work to date, we've used drawn, activated, and recast palladium rods. We have no evidence for neutrons above 10 to the 2 per hour per cubic centimeter palladium in any of these samples. We have stepped and pulsed the current and seen nothing with regard to that either. No evidence for gamma ray production over that range of 20 keV to 30 MeV. No evidence for tritium. We've seen no evidence for helium in the headspace. And we've seen no excess enthalpy produced to within our experimental error of 6% in either H2O or D2O. Thank you.
Question over here. Just a minute. Please wait for the microphone, wherever it is.
Nate Hoffman, ETech, part of Rockwell International. Did you measure the volume expansion of the palladium after you put the deuterium in? And in particular, did you see which ones cracked?
We have not done quantitative measurements of the volume palladium expansion, but we did actually bend some rods to try to cram them into smaller cells, and they unbent. So it's very clear that there was some expansion and some cracking. We also have run rods that were straight and did not do that. We haven't directly quantified the volume expansion, though.
Question over here, please.
I want to make a contribution to Dr. Lewis's talk because I want to tell all of you who are not electrochemists in this audience that Dr. Lewis is well recognized as an extremely competent and excellent electrochemist, and I want to state this to start with and ask why it is that Dr. Lewis and all the people working with him can't replicate these results. Now, it's becoming increasingly clear that you can or you cannot. People get it, some people do, some people don't. It's a phenomenon of great irreproducibility. And if I knew exactly what to do, I would be back at Texas A&M telling them exactly what to do. Because, of course, at Texas A&M, although we've got a lot of results, many of our results have been negative, like Dr. Lewis's. Now, I just want to make, then, 3 points as to why perhaps it is that many people don't get the results that other people do. One, the DPD ratio. I believe it's going to turn out that having the DP ratio more than 1, I can only tell you that Pons told me his were 1.12 or more. I don't know exactly how he did it, but I think it was weighing, may be vital. 2, one point I think everyone has neglected, at least it's been neglected in the last 2 presentations I've heard, is the stress on overpotential rather than current density. It is not enough to say, I have charged at 500 milliamps or whatever it is. It is important to charge at very high current densities if you're going to get important effect, but you must also have a high overpotential. All Pons and Fleischmann solutions were heavily poisoned. And the third one is H very low. It may turn out that H is a poison. I fancy it is. And it may turn out that in many cases people have unconsciously been putting H into the electrodes and thus making it impossible for the D to go in. I think we'll have more of that later on today.
Agreed. Well, let me take these in order. One, let me take them in the middle. You said that Pons and Fleischmann's electrodes were poisoned. There's no public knowledge that I know about that says that's true or what the poison is. If that's true, that would be potentially very important, and obviously that would make a difference. As far as the stoichiometry of deuterium to palladium, we have a potential measurement that might indicate a higher stoichiometry at the surface than in the bulk, and I'm sure that that is true, and perhaps it's that potential measurement that was used by the Utah people to decide the stoichiometry was 1 to 1 or greater. The bulk stoichiometries, all we can say at this point is when the rod is charged at 64 milliamps per centimeter squared, we see 0.8 deuterium to palladium. That's very consistent with what the MIT people reported and with what other people have seen at those current densities, which are also similar to the ones used in the Utah report. The poisoning may affect things. We don't know if that is true. It's certainly true the hydrogen content is important. We've told you our number. If other people are worried about hydrogen in their D2O, I think it would be useful for people that see effects to tell us what the hydrogen content is in their cells so we can compare quantitatively.
Mike Lauenberg from UC Santa Cruz.
Can we have this mic live, please? That's a bit too much. Thank you.
Mike Lauenberg, Santa Cruz. Hi. I want to...
Too close.
Hello?
That's better.
I would like to comment on the comment and then ask a question. Some people do see things and others don't. Now let's talk about those who do see something. Fleischmann, Pons, and we shouldn't forget always to mention Hawkins, who is a collaborator in this experiment. A comment has been made already earlier about the gamma ray spectrum, which doesn't look like a gamma ray spectrum, and I'd like to add a comment about the spectrum which is supposed to give the evidence for tritium decays, which I have seen some, I'm a theoretician, but I have looked at some spectrum that looks like, you know, it's a well-studied spectrum, and that spectrum doesn't look like a tritium spectrum either. So when you say you compare your data with the tritium data of the collaboration in Utah, you should also comment about the spectrum. And I'm wondering if you can tell us, in fact, since I presume you have looked at the background tritium, what do you have a spectrum to show us and how it compares with the...
I can do that.
Because there's no evidence that they have seen any tritium at all. At least I don't understand it.
I could show you the spectrum, and I don't have an overhead right here with me. They're close. They're not identical to what we find. We've placed more faith in the count. Remember, we do not know the background level of the tritium in the Utah results, so we do not know the difference between the background and the foreground. We just know the foreground rate is about 100 decays per minute. Our naturally abundant tritium is higher than that in the background, so we can't quantitatively. All we can say is that our limit on tritium yield is very low. We really have no data at this point to say what the Utah reported yield was. I think that's a fair statement.
I'm talking about the shape.
The spectrum. Yeah, I could quantitatively do that. In fact, sometime I will, not at this meeting, I could get it faxed to me, but I do have the data. They're similar but not identical in shape to authentic tritium samples. Similar but not identical.
Hello. Huggins, Stanford. Nate, I noticed that you annealed at 300 degrees centigrade, or 350. For a material like palladium, this is certainly not anywhere near high enough temperature to get interstitial impurities out of the octahedral or the tetrahedral sites. We have found that we need to remelt our samples 10, 12 times in order to make sure that we clean out some of these interstitial impurities, which you might call poisons. I just call your attention to the fact that if you want to try to clean up your palladium by annealing, you cannot expect to do this at a temperature as low as 300 or 350 degrees centigrade. You ought to be of the order of 80% of the melting point, and melting point is quite high.
We understand that. The only reason we annealed at 350 was to drive out any bulk hydrogen that might have been there from any cold working. The remelted samples were remelted many times back and forth through the melting point under either CO or argon. Some of the samples were RF melted dead soft palladium that are 5/9 purity by Bill Johnson Materials Science. They were melted under argon. To our best estimate, they have very, very little interstitial hydrogen or any other hydrogen.
John Wacker, Pacific Northwest Laboratory. This is really directed towards Professor Bockrus's comments. Most of us in this room, or a lot of us, have tried to duplicate these experiments on the basis of some rather sketchy information. And we've been accused now twice of saying, well, we haven't charged for a long enough period of time, or we haven't used poisons or whatnot. Now, the information that's been alluded to today, for instance, Professor Bockrus, you made a comment earlier that it takes 75 days or 72 days or something like that to charge a a half-millimeter rod of palladium with deuterium. Now, the information we've heard on this earlier ranges anywhere from 10 hours to 160 hours to 800 hours, depending on which news conference that you happen to have heard. And yet this information has never been published from the Pons and Fleischmann group. And now you're telling us that, according to what Fleischmann has told you, that they have a very heavily poisoned solution, whereas they've gotten up at news conferences and said all they do is lithium deuteroxide in their solution. Now, and they don't say anything about this in their paper either. And frankly, and I suspect this sentiment is felt by many people here, we're getting a little bit tired of having science done by news conference. That, you know, we have a workshop here, let's get these things out in the open and figure out, all right, if there is a real effect here with the Pons and Fleischmann type fusion, what are they doing? And if it takes 72 days to do it, that information should be out. If it takes 10 hours, that's the information we should be getting. If it takes a poison, fine. What is it? What conditions are they doing? And that information simply hasn't been released yet, or it's been in little dribbles and drabbles. For a while we were going through a fact of the week, and everyone would rush out to their laboratory again and set up a new experiment based on that new fact. And I think it's time we start clearing the air on these things.
That sounded more like a comment to me than a question. Was that intended to be a question?
Please take this for the discussion section.
Dr. Bachris, once more, and then the rest will stay.
I think that's, I agree largely with the person who's just spoken. I said in my comments, if I knew exactly what to do, I'd be back at Texas A&M doing it. I think we have to find out the conditions. I talked extensively to Fleischmann and Pons. Maybe I've talked to them 6 times, 7 times, something like that. Each time I've had hedged information. They'll give me something, they won't give me something, they say some things, they contradict it. It's not a clear situation. In my own personal opinion, I'll go on record as saying this, and certainly this will get back to them. I don't think they know exactly the conditions themselves. I think they're playing with it and trying to find the right conditions themselves, and I don't think they can always reproduce it. I think they're often very puzzled about the fact that some rods don't work and they don't know why. I think they're only 2 or 3 times better off than we are, so to speak. So we have to find those conditions. But I think the overall point I'm making is that very many people have reported positive results. Many people have reported negative results, and we had to find out what the conditions are.
Simpson?
We have time just for 2 more comments, one here and one on this side.
Okay, to answer the question on the tritium counting and exact shape, and someone from Los Alamos can correct me if I'm wrong, Robert Sherman or someone, that's quite dependent on the instrument you're using.
Right.
Okay, you're dealing with very low light levels, single photon response. The thing you compare is the endpoint, and with a Curie plot or something like that, and you don't expect them to be identical. Now my question to Nate was to get it straight on neutron backgrounds and limits and rates. You said that you have 1.5 neutrons per minute, 75 to 85 neutrons per hour. Does that include the efficiency? Is that total? And can you please show us a frequency distribution of the background runs versus one of these sample runs that had fluctuations that you seem to think are not significant? Can you show us that comparison?
One of those, I did show a run where the background runs were interspersed in between foreground runs.
Have you plotted them out, though, as counts per minute versus...
This is neutrons per hour.
Frequency.
And the dark circles are foreground, or dark indications are foreground run, and then there's a background run, for instance, interspersed. There's a background run, there's a background run, there's a background run, there's a background run.
Now, the one on the right, let's see, the dark circles, that's a real sample.
All the dark circles are real samples.
And the one on the right, how do you tell if there's something there or not? Can you just give us your criteria?
It would be at most 2 sigma for 1 data point.
For 1 data point, yeah. And is that the strongest indication of anything that you have? If it is, I agree, there's nothing there.
That was the strongest indication. I'm not saying this is anything. I think this is not anything.
Right.
That should be the spirit of this view graph.
I agree, you need stronger evidence.
These are neutrons per hour, so this is corrected for the efficiency.
So you're running at a few hundred neutrons per hour.
Right.
Okay.
Yeah.
Tom Schneider, EPRI. Nate, I was curious at the end when you started talking about the calorimetry data, you said that your accuracy was about 6%, and you had seen some excess heat, or you didn't. No. I wasn't quite sure. And the other question, which sort of really is the same question, that then puts an upper bound on any possible recombination of being less than that 6% number.
Well, here's a better summary of what for this particular run. These are the excess heats, excess powers relative to what we believe a reasonable estimate of our errors are in that measurement. And so we would say that we had at most 6% excess power, plus or minus 2%. This is given by standard systematic errors in both the measurement of the thermocouple, in our estimates as to other variables in the cell. These numbers could certainly be accounted for by some small amount of recombination. These are if they were 0, that would be the coolest the cells could ever be given that input power and all the gases escaping. It's very reasonable to assume that not all of the gases escape given that we have platinum and palladium around. We don't absolutely know for certain that this is not excess, but the light water controls have also run typically 4 to 5% excess or what you would expect. I might also point out there's a paper in the literature in 1958 by a well-known calorimetry scientist, Abner Brenner, at the National Bureau of Standards. And in a cell, even with a separator between a platinum and a platinum anode cathode, he found excess powers of the order of 5 or 6% because of small amounts of recombination.
But that really then is an upper bound.
This is an upper bound.
Any potential recombination that you would see, you
Right.
wouldn't really expect to see a lot of it.
Right. We wouldn't expect to see a lot, at least in this particular set of measurements. It's very dependent on the cell, on to whether or not you have some palladium exposed, how rapidly you're stirring, because you're going to mix up the oxygen evolving from the anode back to the cathode. I think if one wants to do this in an open system, you would have to account for all of the gases independently before you could claim 10% differences between an H2O and a D2O cell were actually excess enthalpies. So I would think that these numbers are for a given measurement, but I actually really thought that the Canadian and Oak Ridge calorimeters were much better suited for this purpose than these types of systems. So if I got a 10% difference here, I wouldn't think that that would be evidence for anything.
I'm sorry we've run overtime on this discussion. I recommend that some of these topics be continued this evening. I would like to call for the next paper, Search for Fusion in Deuterated Transition Metals, Dynamical Pressures above 1 megabar. This is a group of people as listed in the program from Los Alamos National Laboratory. I believe the paper's been given by Dr. Mueller. Is Dr. Mueller here, please?
I'll finish in time.
Good afternoon. Recently, there has been a substantially increased interest, both by the media and also by scientists, in the old and declassified field of fusion phenomena. I think much of this interest has been engendered by the hope that perhaps it may be possible to short-circuit the classical and expensive technological approaches which we've used up to this moment and achieve cheap power through simpler means. What I will do in this presentation is to focus on one experiment which seeks to clarify some of the issues and parameters as considered from the point of view of deuterated solids. I caution the audience that at this point we have done one experiment, so we have hardly tested our reproducibility at all. However, in the next presentation in this session, I noted that there is an independent submission to this workshop from the Oak Ridge National Laboratory, and I believe some of the aspects, there's a great deal of similarity and perhaps something of the sort of results of the present experimental focus. But except for revolutionary and unexpected repeal, the laws of nature, whether viewed by physicists, chemists, or metallurgists, would be the same in all experiments. Whether generated by static or dynamical pressure, by particulate implantation, or by strong external exciting electrical fields. Let me briefly review. In the first slide, if I could have the slide and perhaps the lights dimmed, I show the potential acting between any two nuclei. There's a small radius, R0, within which the strong nuclear forces acts. There's also a much larger radius, or region, where Coulomb repulsion dominates, as can be seen. These ideas were first investigated by Gamow and simultaneously by Gurney and Condon in 1928, using the new gadget of theory called quantum tunneling to explain alpha particle emission out of the nuclei. Our present focus in this workshop, of course, is similar but backwards. We want to get things in causing fusion rather than out as in the original alpha emission. Now, if we examine the tunneling probability, which is on the bottom part of this slide, we see that we can possibly alter 3 experimental parameters. We can increase the particulate energy of the 2 nuclei trying to fuse, the parameter E. This has been the classical approach which has been applied for some time now and has been pursued both in the United States, Europe, and in Japan. Also, if one starts thinking about this, one can lower the Coulomb barrier, either through electron or muonic screening. We can also reduce the internuclear separation, big capital R. So the 3 elements for possibly doing that then is called the kinetics, or E, the lowered Coulomb barrier, which I associate with V, and the reduced nuclear separation having to do with R, big R. There's many ways of thinking about doing experiments possibly of this sort. All of these would lead to enhancement, but since we start with such a tough barrier hill to bore or tunnel through, one might not think that there's much chance of success. However, I think here in sunny New Mexico, the sun works every day, but conditions on Earth are simpler but also sporadic. In the next slide, I'm going to examine those 3 themes as projected onto some 10 condensed matter phenomena to see what one might think one could make in order to perhaps have enhanced fusion enhancement phenomena. I'm not going to go over this in any great detail. This will all be in any publication which might emerge from this workshop. Nevertheless, the X's are a relatively large effect, in my opinion. The O's are very small, and the slashes are something in the middle. I point attention to crack propagation, which I think will be discussed tomorrow by some Los Alamos workers, but maybe many others, and perhaps some of the other things where one has crowd ions, dislocations, things being pressed together by metallurgical or solid-state pressures with the point of view of enhanced fusion. I think if you simply take, for example, if I can show the next overhead, techniques where one applies pressure to the system, there's no doubt in my mind that if you fully deuterate a piece of palladium, as I'll show in the next overhead, not yet, one will not have things at a close enough distance to do anything very substantial to the tunneling integral, which I discussed before. One needs other elements or other possibilities, and I think there may be such things. Without tests, how can one say? One element for producing these is to put a great deal of pressure on your system, not very slowly, but as I think has been discussed, dynamically and very quickly, to induce a lot of abnormal and non-equilibrium phenomena. Now here are some 4 techniques for doing high-pressure experiments. And what we're going to focus on in this presentation is not diamond anvils or gas guns or recoverable or magnetic flux compression, but recoverable compaction. The states induced by these are listed in the extreme right-hand corner. And if I can show the next slide, I'll show you what palladium with octahedral deuterium in it looks like. In the experiments which I'm going to discuss, we put in a very modest amount of deuterium, approximately 0.7 deuterium per metalloid site. So you can imagine that the green balls in this palladium simulation are occupied approximately 2/3 of the time. We also had in the experimental chamber, as I'll show in a moment, titanium, 1/10 of a gram of titanium and 3/10 of a gram of palladium. The titanium was also deuterated to approximately 7/10 of a gram, 7/10 deuterium per metalloid site. In the next overhead, or slide, we show the experimental chamber of the fully shock-loaded recoverable system. This is a very complicated engineering drawing. What I wish to emphasize for you here is that one has here explosive, which is a high explosive, which is going to be set off, and I'll show you a little bit about how that's done. That produces enormous pressure, which is focused on the interior and comes screaming into a mandrel in the interior. And one can think of this in layman's kinds of terms as an enormous big circular hammer which is beating down on a small circular anvil and producing lots of shock compaction in the interior. Also associated with this is a bottom plate and a momentum trap which takes all the energy, or a good deal of it, going down so you can recover these systems. Last but not least, the steel top trap, which goes up into the sky, lands 37 seconds later, and therefore it's a homework problem to try and get how high the thing actually went. In the next slide, we show some test simulations produced on the craze by Stan Marsh, in which we're looking at peak pressures which are in the interior of the system. And what we're showing is that at this point in space and time, that there is in megabars, which is the bottom column, spikes of pressure which go to approximately 1.5 megabars. Next overhead. This shows a cross-section through the same thing I just showed you, except now the shock is running up the vertical axis. Out there is the high explosive, and these are contours of constant pressure organized in this structure, and the experimental situation is down in this immediate vicinity. Inside this pressure chamber also is some zinc for doing post-shock neutron activation analysis, and also some titanium foils which are in the interior. So we have a wrap in here of palladium. Outside that little wrap of palladium foil is some titanium, and we're going to put some enormous pressures on that. If I can have the next overhead. This is the little part of the mandrel in the interior, and one has just started to have the shock wave come down from the outside through the explosive and now arrive at the mandrel. In the next overhead, we have the same situation 1 microsecond later. So we're not talking about neutron counts per hour here. We're dealing with phenomena which are happening on very short time scales of a few microseconds. So this is 1 microsecond later, and the height and color of these little spikes are telling you information about the pressure, scaled to the 1.5 megabars that I showed you before, but now associated here with the foil which is being compressed of palladium and of titanium. Next is another microsecond down, and the next is another microsecond down. And I think you start to see here in the next overhead how this is moving down the little mandrel as this focused energy is being forced onto this situation. Next overhead. We wanted to test our detectors, and so we organized a special experiment in not this instrument, but something completely different, a plasma-focused device. And what you can see here is a neutron rate on the vertical scale going up to a height I'll draw your attention to of 20 times 10 to the 15 neutrons per second in a time scale which goes out to a microsecond. These are not unusual results for those experts in the community who have been looking at these sort of things. These are typical results which happen in this kind of an instrument every day. The integrated fluence from here out to the end is 6 times 10 to the 9 neutrons. If I can have the next, we look at the data from the experiment which was conducted the next day, not the 11th, but now the 12th, and the data are plotted here. There are 9,000 data points plotted here every 4 nanoseconds, and of course, as you can see, the screen is pretty well blank. If we expand the scale, however, by a modest factor of 6 times 10 to the 5th, or 600,000, we obtain the results in the next slide. Now, this experiment is a little different than I think any so far presented at this workshop, because here we